All right, guys, I went back and looked at this example to see if this mean was even important down here. In terms of what we're doing, I don't think it's even going to matter. So this is back, typically I do a study in class of shoe size of students in class, and we use our population of our class to determine that. So let's say that population mean back when we did that study was 7.2, standard deviation of that was 2.5. Series of questions about that. Degrees of freedom is the first one. Whenever you're looking at these t-distributions, again, it's a family of curves that you're looking at. You've got to figure out which curve you're going to use to estimate the population. So, oops, sorry for this. So to figure that out, you got to figure out what your degrees of freedom are. We are looking at 15 degrees of freedom because our sample size was 16. That should make sense, which means if I look at my tables, I go down to 16 degrees of freedom, and this set of values will tell me, my confidence intervals if I'm going to use that, which is what I'm asking in part B here. You could do this with technology, with stat key. I really want you to be able to use it with t-tables. So if I'm looking at the 2.5 percentile or the 97.5 percentile, I'm looking at that 0.025. This is really the numbers that allow me to write a 95% confidence interval. That's what I'm after. Tristan, can you turn that down, please? So if I go down to 2.5%, I'll get to this 2.12 is what you'll see on your paper. Hopefully that makes sense. That allows me to sort of draw my curve on here to show what this would look like. And I want to be able to think of what the t-distribution is going to look like this whole entire time. Eventually I'll estimate the standard error, which is pretty easy using that new formula. The probabilities come from these numbers here. Now, eventually, part C is a little trick here. How I'm going to interpret that problem in a minute here, but I know this is going to be centered at 0 if I'm looking at a standard normal curve here, centered at 0. And if I go 2.12 standard deviations to the right and 2.12 standard deviations to the left, that will get me my percentiles, my 97.5 percentile, and my 2.131, because I go up 1 for my degrees of freedom. Sorry about that. That will give me my 2.5% here and my 2.5% here. Hopefully that makes sense where those numbers are coming from. I could get the same thing from stat key. I'm just using the table to interpret that. That's what those numbers in the table represent. This is the number of standard deviations I am. This is the percent. This is like the p-values up here, the percentage of data that falls to the right or to the left above those tabulated values. And I can just think of these negative values with symmetry to get the other side over here. So that's part B. That's my percentiles. So use a t-table to find the 2.5 percentile. Well, that's that many standard deviations away. That's a t-value, another way to say that. Find the probability that t statistic is more than 1.3. So again, these are my t values. I got to find 1.3 in my 15 degrees of freedom column, which is down here at, down here on the left at 0.10. That's like saying it's a 10% chance of that occurring. So I can't get exactly 1.3, but this is the closest I can get with a t-table. T-table is probably maybe not as precise as a z-table because you need so many more numbers in a t-table to show, you need so many more t-tables to show what's in a z-table. One for every curve, one table for every curve essentially. So probability that t statistic is more than 1.3, well, it's about 10%. It's like I'm moving these numbers in a little bit. Maybe that line is over here for 1.3 standard deviations for t. That's about 10% of that data. Hopefully, and this is really just to explain what the heck the table means. T statistics are like z values. The numbers on the top are like p values, but you only have, those 10 p values. You can't get a p value for every single number on there without some technology. Part D should be an easy one. Standard error, that's just your standard deviation divided by the square root of your sample size. Pretty quick, easy one. 2.5 divided by 4, which should be, I believe, 0.625. And then the last question here, is a t-distribution appropriate? So that's what you think about is the data skewed and is the sample size large enough? Well, we didn't have anybody with size 22 shoes or size 1 shoes, so there's no extreme outlier, so we're good in that respect. Sample size is only 16, it's not 30, but it was normally distributed, so we'd say yes, it's okay. If any of those three criteria were not met, we could be messed up on here. Sample size would be too small and it was skewed, that would mess us up. Hopefully that makes sense. I think that's the last thing I have on there for you. The back of the page, just a warm up. I think we're good.